And what I will do is to present work from Quantum AI, Google Quantum AI, which was finished relatively recently, beyond classical quantum simulation. I should say that this work involved a lot of people. I was actually thinking in the old days when Quantum AI was like, Google Quantum AI was like 30 people. We usually customarily created a set of photographs, collective photo for all the 30 people, but now it's what, 400 something. So at this point of time, I have no chance, and I was thinking of AI fusing those faces in one. I decided not to do it. So I want to highlight leads of that project. It's a Xiaomi lead experiment, Kostya Ketiji, who was a theory lead on that project, Tom O'Brien, who was leading algorithms and applications, and also Bin Villanonga and Salvatore Mandra, who are leading high-performance computing. So what is the goal of practical quantum simulation? Probably it's learn something new about the system, which you did not know before, or a loss of nature, or a physics mechanism, uncover something. Now, we specifically have in mind an application of practical quantum simulations, which is Hamiltonian learning. Given a model of Hamiltonian with unknown parameters, choose a value of parameters, and predict an outcome. Now, learning parameters that match the outcome of the experiment is the target. So that's an overall setup, and an example is NMR, nuclear magnetic resonance. Everyone knows that this is a method by taking a spectrum, a line spectrum of individual molecules, and trying to reconstruct molecular structure. In fact, conventionally it is done by suppressing all the interactions between the spins, nuclear spins, so that you can actually see the line spectrum. And that's an example of Hamiltonian learning. Now, let's formulate requirements for Hamiltonian learning that are done in beyond classical regime. So first, efficiently measure an observable with a bounded error, which is complexity class BQP, which is generally verifiable, but we're going to reduce it to reproducible on a quantum computer, which is in QMA. That's statement one requirement. Second, observable must be sensitive to the quantum circuit and parameters, and I should say to microscopic parameters. Because what is important, if I want to learn the structure of the circuit or the parameters of the Hamiltonian, the observable needs to know if I change any of them. Now, and finally, as I mentioned, computing observable should be hard, classically hard, for a typical instance, not just for one particular one. What we're going to show today, both theoretically, numerically, and experimentally, is an example that satisfies such requirements. So let's start from the challenge that emerges as we are trying to satisfy this requirement. Let's consider one known example of a classically hard problem, which is sampling from random circuits. Random circuit composed of 1 and 2 qubit gates, which is what we typically consider, would be of the length square root of n, which is a linear dimension of a qubit array, of the depths. And at that point, circuit becomes really hard. Now, at that point, the circuit generates states which are typically close to the random vector from a Hilbert space. The problem is that if I look for the local observable, and Hamiltonian learning typically deals as an input with the local observables of the physical quantities. Now, the local observables will have values which are exponentially small, or fluctuations are exponentially small from circuit to circuit, 2 to the minus n over 2. And the same goes with typical standard time correlation functions. So in this case, the number of runs of a quantum experiment, the number of shots, has also be exponentially large. So in this case, the problem hard both classically and quantumly. Now, how to avoid that challenge in a complex circuits, especially chaotic circuits that are typically classically hard to compute? How to avoid that challenge of suppressing quantum fluctuations? We propose a new quantity, a correlation operators, and the moment of that operators is the one that's going to give us information. Now, that correlation operator exploits repeated reversal of arrow of time. So let's try to work it out. Let's start by a simple identity. I apply a many-body circuit. U is just a circuit and many-body system, and then I invert it. That's an identity. Let's now stick a perturbation, which we're going to call for a future a butterfly operator. It's a Pauli in our case, single cubes Pauli, somewhere in between. So then what's going to happen, this U and U dagger is going to Heisenberg evolve that butterfly operator, spread it over the space. And then I'm going to insert M, which is a probe, a measurement operator, again, single qubit. And that product, B over Heisenberg evolved B of t times M, represent a correlation operator. And usually, people would measure expectation value of correlation operator. You can recover from here, you recognize it's a standard correlation function. Now, but the correlator operator itself contains way more information than correlation function, which very well could be exponentially small, as we discussed in random circuits. But correlation operator contains more information. So let's think about this. First of all, how we actually implement the correlation operator and measure it on circuits. It's done in the following way. So you prepare your initial state. That is a product state of all zeros, for example, and there is a 1 qubit that is an eigenstate of the measurement probe operator. Then you apply repeated pairs of U dagger B U M. Sorry, it should be dagger. And then you apply it k times. And then you put measurement operator at the end, and then you measure. So that's really a circuit to measure moments of correlation operator. Now, what should I say about this? That the plot which I show below, over here, shows that the behavior of a correlation operator versus time for a given separation between the butterfly and the measurement qubit. And I should say that the typical chaotic circuits without any conservation law, the time that is elapsed equal to the distance between the measurement qubit and butterfly operator divided by butterfly velocity. So in a way, what happens, this plot shows the spreading of the butterfly operator, as well as the scrambling in chaotic circuits. And what happens at a very short time when the spreading has not yet reached the measurement qubit, they commute time evolved butterfly operator measurement qubit. In this case, the moment equal 1. At a very long time, when essentially front are already overspread well beyond the measurement qubit, essentially the correlator operator become completely chaotic, then the moment is 0. And in between, there is a front of the spreading of this operator. And this front is peculiar because it has a different shape for different moments and a more complex shape. So it contains an additional information. And that additional information is what we are after. We are after, because look, if it goes between 1 and 0, somewhere at the front is order 1. So now we have something that is order 1 at sufficiently long times. If you spread with butterfly velocity and you place your butterfly and measurement opposite sides of a system, you're reaching the volume law by the time the front reaches the measurement qubit. Yet the signal is order 1. That's a good thing. So this is something to think about, which we may utilize. Now, in order to think of the information from correlation operator, we would like to think about the correlation operator spectroscopy. Let's consider limit of very high temperature as an initial state, maximally mixed state. In this case, we can replace initial state by the trace. So what happens in this case? Let's consider correlation operator. In fact, it's a unitary in case when B and M are both Paulis. So then what we like to do is to consider eigenspectrum of correlation operator, lambda being an eigenvalues. Then moments of correlation operator, just moments of the spectrum. Now, you can think about this the following way. At the very initial time, when the butterfly and measurement operator commute, then the spectrum is represented, is degenerate, highly degenerate, and represented by 2 points, plus and minus 1, on a unit sphere, because it's a unitary, so the entire eigenvalues are in a unit sphere in a complex plane. Now, when you wait for a very, very long time, when the moments are close to 0, the spectrum is essentially represent a Gaussian, close to a Gaussian unitary, not a Gaussian, just a circular unitary ensemble, sorry. So in this case, the spectrum densely populates the whole circle. Now, in between, as my parameter of the correlation operator, which is time, getting larger and larger, and the front of the operator spreading of butterfly reaches the measurement qubit. In this case, the spectrum begins to close. This spectral gap begins to close. And at a certain point of time, when the measurement operator is somewhere at the front, it closes. So in a limit, if I take a limit of a very large time, and I position my measurement qubit in the relative coordinates relative to some point in the front. So what happens, this transition of closing the gap in physics is associated with a critical phenomena. So there exists a critical phenomenon and a behavior of correlation operator, and this exists somewhere in the front. Now, you can look at the moments of the spectrum and quickly recognize that this closing of the spectrum, existence of the gap or the absence of the gap, is actually revealed by the higher moments of the spectrum, which you need a fourth moment to characterize that, not only a second moment. Good. So what we wanted to understand now with this correlation operator, we know now that the moments are large from the previous node on the front. What we like to understand are what happens with fluctuations. Because the purpose of interest for us, as we said at the beginning, is sensitivity to microscopic parameters. So we take a random circuit. We take a circuit, a random unitary, and pretty much we consider, in this case, 1D brick wall evolution with random single qubit and also 2-qubit gates. And different plots in here corresponds to different distances between butterfly and measurement. And you could see that the fluctuations, circuit-to-circuit fluctuations, are maximum at the front at different distances, which is shown over here. In fact, here we plotted a density plot of standard deviation variance, so you can actually see that this is really centered at the front itself, at the front spread. And what we can do, we can plot standard deviation of different moments as a function of time. And this is a log-log plot, so you could see that the standard deviation is actually polynomially decaying with time. So now we see that there is a strong sensitivity of the quantity of choice, moments of correlation operator, to the circuit-to-circuit fluctuations, which is one of the criteria that we had. Now we would like to understand the classical hardness. Now, what we believe that there is an insurmountable sign problem at the core of the classical hardness of computing those moments, in particular the fourth moment. So let's write down the fourth moment and recognize the following fact. What we're going to do, we're going to expand the time-evolved butterfly operator into the Pauli expansion. So basically, we're going to expand in the basis of the Pauli strings. Each element for a given qubit is element of the Pauli group, identity x, y, or z. And then the indices of that create a composite index alpha, which is the indices of elements of Pauli group on all the qubits, which is a Pauli string over here. So when we expand, this is a quadrupole expansion, generally, for fourth moment of these Pauli strings. And this is a product of what is called a Pauli transfer matrices for each of the power of the correlator operator. And this is a geometrical constraint, which is a trace of product of 4 Pauli strings times measurement operator. Now, we can break that sum on 2 parts. One of them is when the Pauli strings in quadrupole pairwise equal. In this case, the weight, the product of 4 Pauli transfer matrices, is actually product of 2 squares. Now, each Pauli transfer matrix, because Paulis are Hermitian, are actually positive. Sorry, are actually real. They could be positive or negative. But the product of squares is always real. Now, if you have a real, that means you can use it as some effective normalized probability distribution. You can sample from it. Because the trace is confined, that gives an idea of efficient sampling Monte Carlo algorithm to compute that sum. Now, the number of terms in a sum is exponentially large, but because I have probability distribution, under normal assumptions, this probability distribution can be efficiently sampled, sum can be computed. Now, in fact, I can picture that as the path integral, a multiple sum over Pauli passes. Why? Because I can take a Pauli transfer matrix and I can divide that in intermediate slices in time. And for each of them, there will be Pauli strings. So I can do a sum over intermediate Pauli strings that create a Pauli path sum. And because of this property, that when I start at the beginning, I have a butterfly operator, then time evolved and create the sum over Pauli passes. But at the end, because of the geometrical constraint for a diagonal term, for this one, I only can arrive either to one Pauli string PA or to another P delta. So let's consider PA, P alpha. This is the sum over all Pauli passes start at B and up in P alpha. In chaotic evolution, if passes go far away from each other, they have exponentially hard time to unlikely to actually come back. So the passes form narrow tubes. They can intersect and create some path interference, but this path interference is small enough and can be taken efficiently into account by the sampling algorithm, as we show in this our paper. Situation is drastically different in another case where this geometrical constraint is not zero, where all the elements of the Pauli group are distinct, all four. And they create a closed loop in the Pauli group. In this case, what happens, the Pauli passes starting from the butterfly operator all end up in different places. And then they're connected by this loop. In this case, the product of the Pauli transfer matrices could be anything, could be positive, could be negative. It cannot be used for efficient sampling. And this is essentially introduce a very significant sign problem. Now, you might ask, okay, but if I have exponential many terms, in fact, factorial many terms, and all of them different sign, how that happens, in fact, that they end up as a sum, end up in something which is not zero? Well, we compute a standard deviation of those moments, both for off-diagonal part as well as the full moments, second and fourth. And you could see that the off-diagonal part, the one that contained that sign-varying interference, essentially it's a log-log, so it decays algebraically. So the hard part of the problem is actually a signal that decays algebraically. So it can be efficiently measured on a quantum computer, but it's hard classically. In fact, we can have a Monte Carlo, we compare that with experimental data and with exact simulation, and we found that experimental data after error mitigation fit exact simulation, but Monte Carlo gives garbage. The Monte Carlo, the sampling algorithm I described before. So now we can actually ask ourselves the question, whether that sign problem is a significant effect of the Pauli basis, or this is something more generic, intrinsic to the problem. And in fact, what I wanted to illustrate now, that is, it's incipient to the problem itself. So, for example, you consider force moment of correlation operator, you can think of the tensor product of 4 copies of Heisenberg evolved butterfly operator. And this is the object which we would like to focus on. What is interesting, that could be expressed in terms of the invariance when I average over circuits. So if I'm interested, for example, in ensemble averaged of the force moment, which is strictly easier than circuit dependent. In this case, what I'm interested is to observe the time evolution of that butterfly averaged over circuits. Now, in fact, one can show, I'm not going to go into the details, that in this case, I can express that in terms of the invariance. And the invariance reflects the local symmetry. In fact, those invariants exist even before the ensemble averaged. And basically, invariance for each qubit, the invariance is labeled by the elements of the symmetry group as 4 in terms of the 4 copies. And then basically what happened, the uniform product of invariant, the same invariance for each qubit, are constant. they are not changing after 4 replicated unitary evolution. This is absolutely crucial element. No, look, it's very simple. If I have 4 copies of a unitary evolution, by simultaneously changing the order of U and U dagger, I change nothing. This is a property of replicated evolution. It has nothing to do with averaging. It's a fundamental property. This is a symmetry. And that symmetry is reflected in properties invariance. Well, now we can say the following. I can now go back to ensemble average, and I can have an update rule when I basically consider that product at time s plus 1 and express it in terms of the product or tensor product of B averaged over ensemble at time s, times the transfer matrix expressed in terms of this invariance. Now, the number of this invariance per qubit is the size of the permutation group, which is in this case 24, 4 factorial. Now, the total number, because it's 4 U's and 4 U dagger, the total size of the Hilbert space would be 256. So that's a big difference. That's as a compression. And the transfer matrix is a product of transfer matrices for each pairs of qubits in the case of the qubit gates. And this is what we need to compute. They are expressed in terms of this invariance. What is important? That expression involves a Weingart calculus. And the Weingart functions are the ones that actually are important here, and they actually change sign. They are acting on elements of symmetry group, and they change sign. For example, when I apply to a single transposition is negative. When I apply to identity is positive. So what transposition means? That there are regions in space, each of them corresponds to its own uniform values of invariance, and then there is a domain boundary between them, and that domain boundary corresponds to simple transposition of elements. This is one example, and there is many different types of domains. So pretty much this represents a fairly significant sign problem due to the Weingart calculus. What we decided is to check whether that sign problem can be circumvented by Monte Carlo by sampling passes in that space by considering absolute values of transfer matrix. Now, our Monte Carlo algorithm showed that in order to capture the values of that, it's actually extremely quickly divergent. The number of samples needed just blows up. That means that even in the optimal basis, the sign problem is ubiquitous. What we did it now, we showed the demonstration of that phenomena, which is really observable, sensitive, and hard on a quantum computer. We use our newest VLO 103 qubit chip, and that has couplers and it has qubits in it and is defined in a square grid. And we use circuits which are ISWAP-like gates, like our Sycamore gates, and also single qubit gate that are taken from random ensemble. So first I show you the spread of the front of the butterfly operator, where it's a density plot of C4, a force order moment, where I place measurement qubits, we place it at different locations, and then we measure that C4. And you could see that, you could clearly see that there is a front going between 1 and 0, and that front essentially propagates with time. Now, what we focus on, remember, we are looking on circuit-to-circuit fluctuations of a force moment. And you could see that they are, as we shown before, are localized within the front area. Now, what we've shown here experimentally is how off-diagonal part of the force moment, the one that is classically hard, is changing with number of cycles. It's a log-log plot. It's changing essentially, it's a pink color. Compare them to the C4 without of the full C4, which is shown here by this green color. So what is important is this pink color has a higher, it's still algebraic decay, but it does have this oscillation that goes bigger. So this is still very efficiently observable, unlike usual time order, which decays very quickly. So what we did, in order to, I apologize, give me a second. In order to extract experimentally the off-diagonal part, we introduced the essentially parallel twirling. What we did, so let's consider again C4. This is a 2 pairs of U and U dagger. We're going to insert on certain time slice a set of random Paulis. And we're going to insert a different set of random Paulis in a different time slice. Sorry, in one pair of unit dagger, we're going to insert one set of Paulis, random Paulis in some cycle, and in a second pair of unit dagger, we're going to insert another set of Paulis for all qubits in a given certain cycle. And then we're going to average over Paulis. You could kind of see from here that this set of random Paulis twirl away off-diagonal terms in the force moment. So when you do that, you measure a diagonal part, the one that we can capture by essentially a classical algorithm, Monte Carlo. What we did now, we plot a correlation from circuit to circuit, a Pearson coefficient, between the diagonal part and the full moment. In fact, we plot 1 minus correlation coefficient, so that the big values corresponds to weak correlation, and the small values correspond to a strong correlation. With blue dots, we show the plot for the off-diagonal part of C4. And you could see that sorry, not off-diagonal part. We show the plot, the correlation, the 1 minus correlation between the full C4, the one that we measured in an experiment without introducing Pauli twirling, and C4 with introducing a Pauli twirling, which kills interference. So when this correlation, you could see, is fairly weak. What does it mean? It means that once we kill interference, the value of force moment is very weakly correlated with the value of force moment before we killed interference. That means that terms carrying the interference, that off-diagonal terms, are pretty large and significant. By comparison, we considered a second moment of correlation operator, and you could see that, again, 1 minus correlation. That means the correlations are very strong with the terms full and the one that kills interference. That means that the second moment, interference is not significant. For a force moment, it is significant. And this is important because it basically says that C4 is highly sensitive to killing the interference inserting Paulis. Now, this plot over here represents what we call our golden data set. What it means is that we consider the largest circuit with 65 qubits, and we consider 1,050 two-qubit gates with a random single qubit gates. Each point represents a value for a given a value of force moment, for, in fact, off-diagonal element of the force moment. Let's be clear. We subtracted from the full measured force moment the diagonal part, which we computed by Pauli twirling experimentally. We subtracted. So we now measure the off-diagonal element. We measure off-diagonal element of the force moment for every circuit. Now, these error bars, it's essentially error bars on the difference between the error-mitigated force moment experimentally and computed numerically. We don't have numerical computation, right? We shouldn't even say computed numerically, ideal value. We don't have direct access for these values because for circuit of that size, as I will show in a second, no classical algorithm can efficiently compute the force moment. So it is now a question. We went into the regime, and I promise you, I'll show in a moment, that this is a regime where we tried very hard and no classical algorithms can compute. So how do we know those error bars? This is what we did. We went on the smaller sizes where we can actually compute it, like 40 qubits, up to 40 qubits, and we can actually compute it efficiently, the diagonal part of the moment, of the force moment. And we did a variety of circuits, a large number of circuits. And we computed basically a distribution of systematic errors over that variety of circuits. Because there's a systematic error and a sampling error. Sampling error you know, systematic you don't. So we consider a distribution of systematic errors, and we develop a model. It turns out the systematic error has a model of multiplicative error times the additive error, which is shown on that plot. When the signal increases, the error increases in essentially linearly. Now, that has a physics intuition behind that, because the front, which typically spreads with the width polynomial, like t to the 1/2, t to the 1/3, that's much more narrow than the area that is swept by the propagating front. The width of the front is much more narrow than the area that is swept. In this case, the fluctuations of a systematic errors are small compared to error itself. So this multiplicative model is work. In fact, what we found in extrapolation, that the model parameters don't change with size, almost don't change with size. So because of that, we were able to convince ourselves with the signal-to-noise ratio extrapolating procedure, which is shown in our paper, that we can put error bars here reliably. And our signal-to-noise ratio is between 2.5 and 3.5, which you convert to the Pearson coefficient. It's pretty close to 1. And this is you could see that the signal-to-noise ratio essentially doesn't change with the circuit sign. As promised, I wanted to tell you that these circuits of that size cannot be computed efficiently. Now, we did a large variety of algorithms, both algorithms such as standard tensor network contractions, as well as the algorithms which are very tightly specific to those circuits, including modifications of the tensor network contractions, which are taking advantage of the circuits. We spend a very significant time trying to cover the entire domain of algorithms. I suggest we talk about this offline. Here I want to show you a highlight. The most efficient algorithm we found is a tensor contraction algorithm. The standard one is Catendra. The one that developed in-house is TNCO. And what we did, we basically consider a best contraction of that algorithm for the essentially over certain time that we use 1200 CPUs to develop an optimal contraction. So what is happening here, after the contraction happens, we want to give you a number of flops, which essentially happens after optimal contraction on that circuit size. And here we want to show you the runtime of 1200 CPUs that it takes to find this contraction. Now, Catendra, which is a standard one, doesn't contract as efficiently as TNCO. So let's focus only on this fastest contraction. So we found the circuits with the fastest contraction. We want to play against ourselves, right? So this is green line, which is basically TNCO. To give you a rule of thumb, 10 to the 60 flops corresponds approximately 1 second on a larger supercomputer on Frontier in Oregon Nation, so not Oregon, I forgot. Basically, it's 10 to the 60 flops corresponds to about 1 second on Frontier, which is the largest supercomputer. Now, what we are having here is that the circuits of the size we consider takes about 3.2 years per circuit on the Frontier. At the same time, it takes about 2 hours on a quantum computer. So you have a very large separation. And of course, quantum computers would improve as well as the classical computers. This is a snapshot in time of a quantum supremacy has now reached for the local operator observables as opposed to random circuits. The one that essentially could lead to a tangible practical applications. For example, as we established by now, the three requirements which we feel are important for practical applications: efficiently measuring on a quantum computer, sensitivity to individual microscopic parameters of the circuits, and inaccessible classically for a typical instance. Now, we believe that that algorithm, this force moments and the higher moments of correlation operator, will have an application in real life. In fact, it all started with a seminal paper by Alexander Pines and co-authors in 1971 that calls time reversal experiment in dipolar coupled spin systems. Mr. Pines, before he died, made the following statement about NMR. He has a paper, I think, in 1984. He said the following: the entire premise of NMR is to kill dipolar interaction so that from the spectrum you can recover molecular structure. And he said, wait a minute, dipolar interaction is the one that carries information because it depends as a cubic of a distance. Let's keep it, let's use it. So paper by Tom Schuster, Tom O'Brien, and others, Tom O'Brien from our team and others, actually found that you can use moments of correlation operator, which is in that case they use ATOC, to recover the molecular structure because dipolar interaction can be inverted in sign. So you can do this repeated time reversal in NMR, and then you can essentially take NMR data, you can use quantum computer to manipulate and see what arrangements of the spins give you best fit to the data, and then you can essentially solve for dipolar interaction, you can solve for the molecular structure. And this is important that these experiments and NMR actually are done today. You could look, for example, on this paper, measuring out of time order nuclear magnetic resonance. That opens a path in future. With this, I would like to thank you and finish my presentation.
Thank you, Vadim. We have time just for like one or two questions. Maybe can the next speaker set up meanwhile as well? Yeah, let's go.
Thank you very much for the nice talk. I have a question. You show this very nice comparison between classical and quantum results. And correct me if I'm wrong, for a classical simulation, you refer to noiseless simulation, right? Right?
I'm sorry, did you?
For classical simulation, for tensor networks, you consider noiseless dynamics.
Yes.
So, and I would say another way to make this comparison is, for example, to make a noisy simulation of classical simulation, then use the error mitigation, the same error mitigation techniques that you did for a quantum device. So I'm curious, did you try to do this noisy classical simulation and see if it works?
In fact, by doing what you just said, we convinced ourselves that error mitigation works. We did it for smaller sizes. In order to develop a noise model so you can error mitigate your signal, we had to use exactly what you did, what you said.
Yeah, but this 3.2 years, if we now try to do noisy simulation, will
it will be much longer, because noisy simulation will be harder to do.
Well, if we, for example, do instead of tensor networks, we do Pauli backpropagation. We know that, as well, was a paper by Tom Schuster.
But what I'm saying is, in this problem, if you have noise in a system, effect of that noise in the system unobservable is essentially rescaling it. So what you end up at the end is a net result of what happens with the noise after rescaling is observable without noise. And that core of observable is essentially the one that I'm referring to with tensor contraction, which is exponentially hard. Okay. This is a property of the noise acting on chaotic system, that it leads to effective rescaling of observable. And therefore, after the coefficient of rescaling depends on noise. But after you rescale, you get an ideal signal, which is still very hard to compute. And that's what we established with our error mitigation. You can look in the paper.
Okay, maybe ask a question later.
Okay.
Okay, let's thank Vadim.